Okay, Assalamualaikum and welcome back. We are still in the chapter 3 gas absorption. So we have some cause and outcome to meet, which is number 5. We need to calculate the number of theoretical stage in a multi-stage counter current operation. So we are in the final weeks for this chapter. Okay, so for your calculations of your multiple stage is actually covered in your plate tray column or plate tower. So first we go for the how the operation in the tray column for the gas absorption. It is still the same with your packing pack column tower. There are still your liquid come from the top and your gas from the bottom, and it will meet in the column at the plate. So the purpose of having plate or packing is actually to make a contact between your liquid and also your gas. That's how the separation can occur if they have sufficient time of contact. So the process should be a counter currently, and the conductivity occurs in the tray, on the tray. So your liquid will flow parallel to the tray, whereas your gas will flow perpendicular to the tray. Okay, so your gas actually contacting with the liquid because of your tray having some holes on the tray. Okay, there are several types of trays. So we have sieve tray, bubble caps, and also the valve tray. So each of these trays have certain purpose and applications to meet the design requirement. So there will be reasons why we use sieve tray, bubble caps, and the valve trays. So the purpose of the designs of the tray also depends on what we want, whether it want to be used as the absorber or as the stripper. And the main focus of these trays, we want to calculate the stages of the tray. As compared to your packing, we are calculating the diameter of the tray. Okay, so we go for the types of the tray. So for the sieve tray, we have the flat perforated plate design. So you can see here there will be some holes on the plates. Okay, it is usually used to make because of their good anti-foulings and also the pressure drop characteristics. So that's why we use the sieve tray. And also it operates under specific velocity range, and therefore would not be able, what will be not a good choice if radical turn down is required. So it is operated at the specific velocity range. Okay, for the bubble cap tray, you can see here it will like the cap on the plates of the tray. So it is applied for the low liquid loading and also large variations in vapor loading for the pack tray. So the capacity is between 10 to 20, and they are superior in their leak-proof characteristics. So bubble cap come in a wide range of design and shapes. Okay, lastly for the valve tray, so it contains a movable valve here. So we have valve on the plate of the tray. Okay, so this valve is offer varying performance benefit based on the specific design requirements. So it is recognized by its integral formulates and can be offered a flush seated and non-rotating. So each design of tray is dependent on the design requirement for the chemical or material used inside of the column on its velocity and also the loading. So we go for the determining stages for the plate or tray tower. So in order for you to determine the stages, we use the graphical method. It's called as the McCarthy method. So there are two lines that we need to draw on this on the graph. So we have the equilibrium line and also the operating line. So before we obtain this line, we need first to draw the schematic diagram of the tray. So if you can remember that your liquid come from the top, so usually we represent our liquid by L0, which is your solvent liquids. And also we have the feed for your mixtures gas, where we have mixtures of A and B. So from the streams of the mixture gas, we will obtain our raffinate. Okay, raffinates, which is we have less of A here, because of the A will contact with the or the A from the feed gas will contact with the liquid of solvent here and will be absorbed and come out as the extract composition in the stream Ln. So from here, by understanding the questions, so you need to come up with all the compositions for each of the stream. So that's mean you need to have your A, B and C components here. Okay, so usually to draw the graph, so we are interested with your compositions of your A and your compositions of your C to plot the graph. Okay, so okay, proceed. So the overall mass balance, to calculate overall mass balance is where we make some summations of in and out, and then we can obtain the value that will be asked from the questions. So the first thing is, in order for you in the question, so usually they will be giving you the data for the equilibrium line, whether you obtain from the equilibrium composition data here, or you need to use the equations of the equilibrium. So it is depends on the questions what is given. Okay, so from here, after obtaining all the compositions here, that's mean you need to have the compositions of composition for your top and bottom here. So you need to have this composition in order for you to plot this graph. So for your graph, there will be more fractions of A. For the more fraction of A, also more fraction, all of them is the more fractions of A. Okay, so equilibrium line you will obtain from the data here. So you just need to plot the line. So if it is not given data, you will use any number of x. So you put, for example, 0x, so by times 1.9 you will get the 0. So you need to plot the graph. Okay, for your operating line, so we need to have the compositions for both of these data. Okay, so for your so actually for your bottom coordinate of the bottom can be obtained from these top compositions. For your coordinate of your top can be obtained from your bottom composition here. So the composition that we require is the compositions of A. So you need to have your A composition at y n plus 1 and also a composition of xan. So that's how you have your x and y composition for each. So you, after obtaining this composition, so you need to plot the line. So you need to plot here and top. So you need to make line connecting between the top and bottom. So after obtaining this line, then you can calculate the stages where we start from the bottom. So you start from the final composition here, and then you calculate the stages. Okay, 1, 2, 3, 4. So if your stages stop here and you cannot have a perfect stages, so for example we start at 3 here, so it's you need to divide A, okay, 3 plus A times B. So your A here and your B here. So that's how you calculate the stages. Okay, the difference between the graph for the absorption and stripping is your equilibrium line is at the bottom for the absorption and stripping at the top. Okay, so usually we're focusing on the calculation of the tray for the absorptions. Okay, so we go for the exercise. Okay, when you have your questions, so first you need to draw a schematic diagram for the system. So you need to have your Bm plus 1, L naughts, and also the compositions for L1, sorry, Ln, and also the V1. Okay, so how we get the information is the answering the question. A tray tower is used to remove 90% more of acetone from air using pure water. First you need to determine A, B, C. A is your acetone, B is your air, water is your C. Okay, that means 90% more of acetone are being removed using water from the feed stream, so 90%. Okay, so the gas stream flow rate is 40 kmol per hour. So Vm plus 1U is your 40 and contain 11% more. That means your Y Am plus 1 is 0.11. Okay, and water flow rate is 100 kmol per hour. L naught U 100 km per hour. The equilibrium data of the system is y equal to 1.9x. So you can use any value of x and then you will obtain your y using the equilibrium data, and then you need to plot the graph. So you need to plot graph of y versus x, and then you will have your equilibrium line and also the operating line. So you need to get the composition top and bottom here. So having the composition, then you can proceed with the calculating of the stages. So how you obtain the molar flow rates in raffinate and extract is from the calculations of mass balance just now. If you have all the composition, then you can put in the component balance calculation. Composition in extract and raffinates you obtain from the calculations, balance calculation, you already learned during CPP. And lastly, the stages is obtained from the graph, plotting of the graph. Then that's how you calculate the stages. Okay, so I will show you how you calculate your Ln. So you know that 90% of A from Bm plus 1. Where is your flow rates of Bm plus 1, 40. Your A composition 0.11. Okay, so that's how you get your compositions of A at here. Okay, I think I will show you more on the next video. I will give one example, and until that, thank you.